There is an object moving through space right now that was built by human hands, launched from Earth nearly 50 years ago, and has never stopped traveling. It is smaller than a family car. It runs on less electricity than a few household light bulbs, and it is farther from Earth than anything humanity has ever sent into the cosmos. Tonight, we are going to follow that journey. But the most remarkable thing about Voyager is not how far it has traveled. It is how little progress that distance represents against the scale of the universe itself. After half a century of continuous motion, after crossing the boundary of our solar system and entering interstellar space, Voyager has revealed something quietly unsettling about reality. Space is far larger than our minds naturally imagine. At Sleepy Time Universe, we explore the science of space slowly and without hurry. For curious minds that need a place to rest. The spacecraft is called Voyager 1. It launched in the autumn of 1977, part of a twin mission that represented one of the most ambitious scientific endeavors in the history of human exploration. In the decades since, it has traveled through the outer solar system, past the giant planets, through the boundary regions where the sun's influence fades, and into the space between the stars. It is the most distant human-made object ever built, and it is still out there, still moving, still sending faint signals home across a distance so vast that those signals, traveling at the speed of light, take more than 22 hours to reach us. That last detail is worth sitting with before we go any further. The speed of light is approximately 300,000 kilometers per second. Nothing in the universe travels faster. A beam of light leaving Earth reaches the Moon in about 1 1/3 seconds. It reaches the Sun in roughly 8 minutes. It crosses the entire inner solar system in under half an hour. And yet, a signal from Voyager 1, traveling at that same impossible speed, takes more than 22 hours to arrive. That is the distance we are talking about. That is the scale of what this spacecraft has crossed. And yet, the most surprising part of Voyager's story is still ahead. Crossing the outer solar system, reaching interstellar space, and becoming the most distant object humanity has ever built might sound like the completion of a journey. In reality, it is barely the beginning. The nearest star remains tens of thousands of years away. The galaxy stretches far beyond that, and the distances Voyager has already crossed, extraordinary as they seem to us, are only the first small steps into a universe whose scale is far larger than human intuition was ever built to grasp. Get comfortable. Let's begin. Chapter 1. The Launch Window. In the mid-1970s, a small group of scientists and engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, were working against a deadline unlike any other in the history of space exploration. It was not a deadline set by a funding committee or a political calendar. It was set by the solar system itself. The outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, were drifting into a geometric alignment that occurs only once every 176 years. In that alignment, a spacecraft launched from Earth could use the gravity of each planet in sequence, swinging from one to the next without additional propulsion, conducting a grand tour of the outer solar system in a single continuous journey. The window to attempt this would open in 1977 and remain viable for only a matter of weeks. Miss it, and the next opportunity would not come until the 2150s. The trajectory had been identified in 1965 by a young aerospace engineer named Gary Flandreau, who was working at JPL as a summer student. Flandreau was evaluating possible routes for future outer planet missions when he noticed the alignment forming in the late 1970s. He calculated that a spacecraft using gravitational assists, the technique of using a planet's gravity to accelerate and redirect a probe rather than relying on onboard fuel, could visit all 4 outer planets in sequence. The geometry was precise to a degree that seemed almost unlikely. A small error at Jupiter would compound into a significant miss at Saturn. But if the trajectory was calculated correctly, a single spacecraft could complete in roughly 12 years what would otherwise require several decades of separate missions, each with its own launch vehicle and its own years of travel time. NASA began serious planning in the late 1960s. The full Grand Tour concept was eventually scaled back due to budget constraints, and what emerged was a more focused mission primarily targeting Jupiter and Saturn, with the possibility of extending to Uranus and Neptune if the spacecraft survived long enough. 2 probes would be built, nearly identical in design, providing redundancy and the opportunity to gather data from slightly different trajectories. Voyager 2 lifted off first, departing Earth on August 20th, 1977, aboard a Titan III rocket from Cape Canaveral, Florida. Voyager 1 followed 16 days later, on September 5th, 1977, placed on a faster and more direct path that would allow it to reach Jupiter ahead of its twin, despite launching second. The naming reflected intended arrival order rather than departure order, a small detail that has caused mild confusion ever since. Voyager 1, despite leaving Earth after Voyager 2, was always designed to arrive first. Each spacecraft was built around a central 10-sided aluminum frame, roughly the size and mass of a small car. From that core extended a series of booms and platforms carrying scientific instruments, magnetometers to measure magnetic fields, plasma detectors, cosmic ray sensors, and cameras capable of resolving surface features on distant planetary moons in detail never previously achieved. A large parabolic dish antenna, nearly 4 meters across, dominated the upper structure of each spacecraft, permanently oriented toward Earth to serve as the primary communication channel for what would become a journey of decades. Power was one of the most critical design problems. Solar panels, the standard choice for spacecraft operating in the inner solar system, were not viable at the distances Voyager would travel. Sunlight diminishes with distance according to the same inverse square law that governs all radiation. Twice as far means 1/4 the intensity, 3 times as far means 1/9, and so on without end. At the distance of Jupiter, sunlight is already roughly 25 times weaker than it is at Earth. At Saturn, 50 times weaker. Beyond the outer planets, solar power becomes effectively impractical for a probe of Voyager's energy requirements. The solution was nuclear. 3 radioisotope thermoelectric generators mounted on a boom extending away from the main body. These devices contain pellets of plutonium-238, a radioactive isotope that generates heat as it decays. That heat was converted directly into electricity through solid-state thermoelectric elements with no moving parts, producing at launch approximately 470 watts of electrical power per spacecraft. Modest by terrestrial standards, sufficient, carefully managed, to power a machine across the solar system and beyond. The launch itself proceeded as planned. The rockets performed as expected. The spacecraft separated cleanly. Within hours of leaving Earth, Voyager 1 was already further from home than most people travel in a lifetime. It would not stop accelerating for years, as the gravitational pulls of the planets it approached added to its velocity through each encounter. By the time it finished its planetary work and began its long outward cruise, it would be moving at roughly 17 kilometers per second relative to the Sun. fast enough to cross the continental United States in under 4 minutes, and still nowhere near fast enough to reach another star within any time frame a human civilization could meaningfully contemplate. What the engineers at JPL had built, without fully intending to, was something that would outlast the careers of everyone involved in its creation. The mission had a defined scientific scope. It had a planned duration. It had a team of people who understood, in a general way, that the spacecraft would continue traveling after their work was done. What none of them could fully anticipate was the degree to which that continued traveling would, over the following 50 years, become a quiet mirror held up to the scale of the universe, a scale that reveals itself not through dramatic revelation, but through the slow, patient accumulation of distance and time. The window that Gary Flandreau identified in 1965 did not wait for anyone to be ready. It opened, the spacecraft launched, and the journey began. Everything that followed was a consequence of that narrow opening in the geometry of the solar system, seized by a group of people working at the limits of what their technology could achieve, sending two small machines outward into a darkness they could calculate but never truly measure until something was actually moving through it. Chapter 2. The Grand Tour. The first destination was Jupiter, and what Voyager found there surprised nearly everyone who had spent years preparing to receive the data. Scientists had expected the encounters to refine existing models of the outer planets. They had good telescopic observations, reasonable theoretical frameworks, and a set of predictions about what the instruments would find. What they received instead was a sequence of discoveries that made clear how incomplete those predictions had been, and how different the outer solar system looked up close compared to what could be inferred from Earth. Voyager 1 reached Jupiter in March of 1979. The images it returned during the approach phase alone were unlike anything previously captured. Jupiter's atmosphere, seen from Earth as a series of parallel bands and occasional oval features, resolved under Voyager's cameras into an extraordinarily complex system of clouds, currents, and storms moving at different speeds and in different directions at different latitudes. The Great Red Spot, a storm system that had been observed from Earth for centuries, was revealed in detail that made its sheer scale difficult to absorb. It was not simply a large weather feature. It was a rotating system larger than the entire Earth, with internal structure, layered cloud formations, and lightning flickering in the depths below the visible surface. But it was Jupiter's moons that produced the most consequential findings of the encounter. Io, the innermost of the 4 large Galilean moons, was discovered to be the most volcanically active body in the solar system. Voyager 1's cameras captured an eruption in progress, a plume of material rising hundreds of kilometers above the surface, visible against the black of space behind it. This was the first time active volcanism had been observed anywhere other than Earth. The heat driving those eruptions did not come from radioactive decay in Io's interior, as it does on Earth, but from tidal forces. Jupiter's immense gravity, pulling constantly at Io, while the gravitational influences of the other large moons pulled in slightly different directions, continuously flexed and compressed the moon's interior, generating enormous amounts of frictional heat. The result was a surface in constant violent renewal, covered in sulfur compounds and lava flows, unlike anything in the known solar system. Europa, the next moon outward from Io, told a quieter but equally significant story. Its surface was smooth and bright, crisscrossed with a network of lines and fractures that suggested the ice above was moving, cracking, and refreezing over time. The leading interpretation was that beneath the surface ice lay a global ocean of liquid water, kept from freezing by the same tidal heating that made Io volcanic. The implications were considerable. If Europa harbored a liquid ocean beneath its frozen crust, it also harbored the basic physical conditions that have, on Earth, proven sufficient for life to emerge and persist. Voyager did not answer that question. It raised it clearly and unmistakably, and left it for future missions to pursue. That pursuit continues to this day, with dedicated spacecraft designed specifically to characterize Europa's ocean and assess whether it could support biology. After Jupiter, Voyager 1 continued to Saturn, arriving in November of 1980. Saturn's rings, always striking when observed from Earth, became something entirely different under Voyager's cameras. What had appeared from a distance as a few broad bands resolved into thousands of individual ringlets, some sharp-edged, some braided, some maintained by the gravitational influence of small moons embedded within them. The complexity far exceeded what the existing models had predicted. The rings were not a simple static structure. They were a dynamic, constantly evolving system shaped by interactions between particles, between ringlets, and between the rings and the moons orbiting nearby. Saturn's moon Titan presented a different kind of mystery. Known before the encounter to have an atmosphere unusual for a moon, Titan was studied in particular detail during Voyager 1's Saturn flyby. What the instruments found was a thick, opaque haze of nitrogen and complex organic compounds that completely obscured the surface. The atmosphere was denser than Earth's. The chemistry occurring within it was elaborate. The surface itself would remain hidden until the Cassini mission arrived decades later and deployed the Huygens probe directly into Titan's atmosphere in 2005, revealing a world of hydrocarbon lakes and river channels carved by liquids far colder than water. Voyager 1's trajectory after Saturn carried it upward and out of the plane in which the planets orbit, ending its planetary encounters and beginning its long outward cruise. From that point forward, its path was set. It would not approach another planet. It would not make another close observation of any world. It would simply travel outward, instruments running, antenna pointed home, crossing distances that would accumulate over the following decades into something almost beyond calculation. Voyager 2 continued on its own path, moving more slowly but carrying the possibility of reaching the two outermost planets. At Uranus, encountered in January of 1986, Voyager 2 found a world of quiet strangeness. The planet rotates on its side, its rotational axis tilted at nearly 90 degrees relative to its orbit, so that its poles experience decades of continuous sunlight, followed by decades of darkness. Its magnetic field is dramatically offset from its rotational axis in ways that remain not fully explained. 10 previously unknown moons were discovered during the flyby, along with evidence of geological complexity on the small moon Miranda that suggested a violent history of disruption and reassembly. Neptune, the final planetary destination, was reached in August of 1989. It was the most distant planetary encounter in the history of space exploration at that time, and it did not disappoint. Neptune had an active atmosphere with wind speeds among the highest measured anywhere in the solar system. A large dark storm system in the southern hemisphere drew comparisons to Jupiter's Great Red Spot. The large moon Triton orbited in the wrong direction, retrograde relative to Neptune's rotation, indicating strongly that it was a captured body rather than one that had formed alongside the planet. Triton's surface had active geysers erupting from it, driven by the warming of nitrogen ice in the faint sunlight at that extreme distance. It was cold and strange, and, in its way, extraordinary. With Neptune behind it, Voyager 2 joined Voyager 1 on the long outward journey. The planetary chapter of the mission was complete. No other spacecraft has visited Uranus or Neptune since. The images and data returned by Voyager 2 during those brief flybys remain, decades later, the primary close-range scientific record of those two worlds. Everything we know about them in detail, we know because a spacecraft launched in 1977 on a trajectory calculated by a summer student in 1965 happened to survive long enough and function well enough to complete a journey that has never been repeated. What came after the planets was something different in character entirely. The encounters had been defined by targets, specific worlds, specific moons, specific questions with specific answers. What lay ahead was defined instead by absence. The spacecraft were now moving into regions where there were no targets, no close approaches, no dramatic data returns. There was only the slow accumulation of distance, the gradual fading of the sun behind them, and the long, quiet transit toward boundaries that had never been crossed and whose precise location was not yet known. The grand tour was over. The larger journey was just beginning. Chapter 3. Leaving the planets. After Neptune, the solar system does not simply end. It thins. The density of material decreases gradually. The sun's light grows fainter with each passing year, and the environment becomes quieter in ways that instruments can measure, but that are difficult to translate into ordinary experience. Both Voyager spacecraft were now moving through this thinning outer region, and they would continue moving through it for decades before reaching anything that could meaningfully be called a boundary. The region beyond Neptune is not empty. It contains a broad belt of icy objects, remnants from the formation of the solar system, orbiting the Sun in a flattened disk that extends from roughly 30 to 50 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers. The belt of icy bodies beyond Neptune is named the Kuiper Belt, after the Dutch-American astronomer Gerard Kuiper, who suggested in 1951 that such a population of objects might exist in the outer solar system. The belt was not confirmed observationally until 1992, when the first Kuiper Belt object beyond Pluto was detected. Since then, thousands have been catalogued, ranging in size from small rocky fragments to objects large enough to qualify as dwarf planets, with Pluto itself among the largest known members. The Voyager spacecraft did not travel through the densest part of the Kuiper Belt. Their trajectories carried them at angles that avoided the main concentration of objects, but they were passing through a region where the solar system's ancient building material still drifted in cold orbits, largely unchanged since the planets formed roughly 4.5 billion years ago. These objects are preserved in a kind of permanent deep freeze, too far from the Sun to experience the warming that drives geological activity on inner solar system bodies. They are, in a sense, fossils, physical remnants of the original disk of gas and dust from which everything in the solar system, including the Earth and everything on it, was eventually assembled. As both spacecraft moved outward through the 1980s and 1990s, the instruments aboard them continued to function, sending back measurements of the environment through which they were passing. The solar wind, the continuous stream of charged particles flowing outward from the Sun, was still detectable, still pushing outward in all directions. The Sun's magnetic field, carried along by the solar wind, was still present, still organizing the local environment in ways the magnetometers could track. But both were growing weaker with every passing year. The solar wind was thinning as it spread across an ever larger volume of space. The magnetic field was fading gradually into the background of the surrounding interstellar environment. The scientists monitoring both spacecraft understood that they were approaching something, even if the precise nature and location of that something remained uncertain. Theoretical models had long predicted that at some distance from the Sun, the solar wind would encounter the interstellar medium, the diffuse gas and magnetic fields that fill the space between star systems, and that this encounter would produce a series of distinct boundary regions. But no spacecraft had ever traveled far enough to reach those regions. The predictions were based on theory and indirect observation. What Voyager would actually find there remained genuinely unknown. There was something quietly remarkable about this phase of the mission that is easy to overlook when focusing on the more dramatic moments of planetary encounters or boundary crossings. Two spacecraft, built with 1970s technology, were operating in a region of space no instrument had ever sampled. The data they were returning had no precedent. Every reading was new information, adding detail to a picture of the outer solar system that had previously existed only in theoretical models and educated inference. The scientists receiving that data understood that what Voyager was doing could not be quickly repeated. No other spacecraft was on its way to the outer solar system. The measurements being taken in those years were, for the foreseeable future, the only measurements that would ever be taken from that distance in that environment. During this long transit, the spacecraft themselves were aging in ways that required constant management. Systems that were no longer needed had been shut down to conserve power. The cameras, which had served their purpose during the planetary encounters, were turned off permanently to free up the electrical budget for instruments more relevant to the outer solar system environment. The radioisotope thermoelectric generators that powered each spacecraft were producing less electricity with each passing year, as the plutonium fuel inside them slowly and predictably decayed. Engineers at the Jet Propulsion Laboratory managed this slow decline carefully, making decisions about which instruments to keep running and which to sacrifice, always with the goal of preserving the most scientifically valuable sensors for as long as possible. The attitude control system, responsible for keeping each spacecraft's large dish antenna pointed accurately toward Earth, required periodic thruster firings to maintain correct orientation. These firings consumed propellant, another finite resource that had to be managed across a mission timeline measured not in months, but in decades. Every decision made about how often to fire thrusters, how precisely to maintain pointing, and how aggressively to manage power consumption had consequences that would not fully manifest for years or even decades. The team was, in effect, making engineering decisions whose outcomes they would never personally witness, for a spacecraft that would outlast not just their involvement in the mission, but, in many cases, their own lifetimes. The outer dark, as those years of quiet transit might be described, was not a dramatic phase of the mission by any conventional measure. There were no planetary flybys, no close approaches to moons or ring systems, no images of alien landscapes being transmitted back to waiting scientists. There was only the gradual accumulation of data points, the slow passage of distance, and the knowledge that somewhere ahead, the boundary regions of the solar system were waiting to be crossed for the first time in history. What makes this period worth dwelling on is not what happened during it, but what it represents about the nature of the journey. The Voyager spacecraft were not rushing toward a destination. They were traveling through a region so vast that human concepts of travel barely apply. The distances involved do not compress with familiarity the way terrestrial distances do. A road driven 1,000 times still takes the same amount of time to drive. The outer solar system does not become smaller or more manageable through repeated crossing. It simply is what it is. A volume of space so large that the fastest machines humanity has ever built required decades to traverse even its inner portions. This is the first lesson that the Voyager journey teaches, and it is one that becomes more insistent with every passing year of the mission. Distance in space is not like distance on Earth. It does not yield to effort or technology in any straightforward way. It accumulates quietly and without limit, and the further a spacecraft travels, the more clearly that accumulation reveals the true scale of the universe in which we exist. The planets, extraordinary as they prove to be up close, are still neighbors. The space between stars is something else entirely, and reaching it would take Voyager not years but decades of continuous travel at speeds no human being has ever experienced directly. The long, quiet transit was the journey becoming what it truly was, not a mission to specific destinations, but a slow crossing of a vastness that had no name until something was actually moving through it. Chapter 4. The Edge Defined. To understand what the Voyager spacecraft were approaching as they moved through the outer solar system, it helps to understand what the Sun actually does to the space around it. The Sun is not a passive object sitting quietly at the center of the solar system, warming the planets with its light and otherwise leaving the surrounding environment undisturbed. It is continuously active, continuously producing, continuously pushing outward in all directions. And the most significant thing it pushes outward is not light, but a stream of charged particles that fills an enormous volume of space and creates what is, in effect, a vast bubble of solar influence extending far beyond the outermost planets. This stream of particles is called the solar wind. It originates in the Sun's outer atmosphere, a region known as the corona, which reaches temperatures of several million degrees, far hotter than the visible surface of the Sun beneath it. The reasons for this temperature difference are still not entirely resolved and remain an active area of research in solar physics. But the consequence is clear. At those temperatures, the particles in the corona have enough energy to escape the Sun's gravity entirely. They flow outward in all directions, a continuous current of electrons and protons moving at speeds typically between 300 and 800 kilometers per second, filling the space around the Sun with a thin but measurable plasma. This solar wind does not simply flow outward and dissipate at some arbitrary distance. It keeps going, filling an enormous volume of space with the Sun's material, carrying with it the Sun's magnetic field, which is stretched and wound into a broad spiral shape by the Sun's rotation. This combination of solar wind plasma and embedded magnetic field creates the heliosphere, a vast bubble of solar influence that surrounds the entire solar system and extends far beyond the orbit of Neptune, far beyond the Kuiper belt, into regions of space that no telescope can image directly, and that, before Voyager, no instrument had ever sampled. The heliosphere is not a small structure by any measure. At its widest, it extends somewhere between 80 and 100 astronomical units from the Sun, in the direction facing into the flow of the interstellar medium, and considerably further in the opposite direction, where the solar wind pushes out a long trailing structure that stretches behind the solar system like a tail. The exact shape and dimensions of the heliosphere have been subjects of ongoing research and revision, and the data returned by both Voyager spacecraft over decades of travel has contributed significantly to refining those estimates. The heliosphere is not a perfect sphere. It is an asymmetric, dynamic structure, shaped by the Sun's movement through the galaxy and by the varying pressure of the interstellar medium pressing in from outside. Inside the heliosphere, the environment is dominated by the Sun. The solar wind fills this space with a thin but measurable plasma. The Sun's magnetic field organizes the behavior of charged particles throughout the region. Cosmic rays, high-energy particles arriving from outside the solar system, are partially deflected and absorbed by the heliosphere, so that the interior of the bubble is somewhat shielded from the full intensity of interstellar radiation. This shielding effect is one of the heliosphere's most significant properties from the perspective of life on Earth. Without it, the level of high-energy particle radiation reaching the inner solar system would be considerably higher than what living organisms here have evolved to tolerate. The boundary of the heliosphere is not a sharp line. It is a transition zone, a region where the solar wind gradually gives way to the interstellar medium. But within that transition zone, physicists had long predicted the existence of several distinct features, places where measurable changes in the environment would signal a shift from one regime to another. The first of these features, moving outward from the Sun, is called the termination shock. This is the region where the solar wind, having traveled outward at supersonic speeds for billions of kilometers, first encounters the resistance of the interstellar medium and is forced to slow down abruptly. The slowing is not gradual. It happens across a relatively narrow boundary, producing a shock wave, a feature familiar from fluid dynamics, where a supersonic flow transitioning to subsonic conditions does so suddenly rather than smoothly. On the near side of the termination shock, the solar wind moves fast, thin, and relatively cool by plasma standards. On the far side, it is slower, denser, and considerably hotter. Beyond the termination shock lies a region called the heliosheath, the outer layer of the heliosphere, a zone of compressed and turbulent solar wind material that extends from the termination shock outward to the heliopause. The heliopause is the true outer boundary of the Sun's domain, the place where the solar wind's pressure finally balances the pressure of the interstellar medium pressing inward, and where the Sun's direct physical influence effectively ends. Beyond the heliopause lies interstellar space, not a destination in any meaningful sense, but a medium, a thin and ancient plasma threaded with magnetic fields and cosmic rays extending in all directions for light years between the nearest stellar systems. This is what both Voyager spacecraft were slowly approaching across the 1980s, 90s, and 2000s. This is what waited beyond the long, quiet transit of the outer solar system. All of this had been predicted, modeled, and debated for decades before any spacecraft came close enough to test the predictions directly. The models agreed on the basic structure, but differed significantly on the details. The distances involved, the thickness of the various boundary regions, the precise nature of the heliopause, and how abruptly it would mark the transition from heliospheric to interstellar conditions. Theory could describe the shape of the boundary in general terms. Only a spacecraft actually moving through it could reveal what the boundary was like in practice. Voyager 1 crossed the termination shock in late 2004 at a distance of approximately 94 astronomical units from the Sun. The crossing was not announced by a single dramatic instrument reading. It was inferred from a pattern of changes across multiple systems, a sharp drop in solar wind speed, an increase in magnetic field strength, a rise in plasma temperature, that together matched what the models had predicted would happen at the shock boundary. The heliosheath that lay beyond it proved to be thicker and more complex than many predictions had suggested, a churning, turbulent region of compressed solar material that would take both spacecraft years to traverse. Voyager 2 crossed the termination shock in August of 2007 at a distance of approximately 84 astronomical units, closer to the Sun than Voyager 1's crossing point, a difference that confirmed the heliosphere's asymmetry and provided the first direct evidence that the termination shock is not a uniform sphere, but a structure whose distance from the Sun varies with direction. The heliosheath that both spacecraft then entered turned out to be scientifically rich in ways that had not been fully anticipated. The magnetic field within it was more variable and complex than models had suggested. The behavior of energetic particles was more complicated than expected, with competing flows of particles moving inward and outward simultaneously. The region was neither cleanly solar nor cleanly interstellar. It was a mixing zone, a buffer between two fundamentally different plasma environments, and it was stranger and more interesting than the theoretical descriptions had prepared scientists to find. Both spacecraft spent years traversing the heliosheath, instruments running, data returning across ever-increasing distances, building up the first direct observational record of a region that had previously existed only in equations. What waited on the other side of the heliosheath was the heliopause, and beyond that, for the first time in the history of any object built on Earth, true interstellar space. Chapter 5. Crossing the Boundary. The heliopause did not announce itself cleanly. That is perhaps the first thing worth understanding about what both Voyager spacecraft encountered as they approached the outer edge of the Sun's domain. The boundary that theorists had described for decades in relatively simple terms, a surface where solar wind pressure balances interstellar pressure, a line where the Sun's influence ends and interstellar space begins, turned out to be more subtle, more variable, and more interesting than any single clean description could capture. For Voyager 1, the approach to the heliopause was a process that unfolded over months, marked by gradual changes in the readings from multiple instruments rather than a single decisive event. The cosmic ray detectors were among the first to signal that something was changing. Throughout the spacecraft's transit of the heliosheath, these instruments had been measuring two distinct populations of high-energy particles. One population consisted of particles that originated within the heliosphere itself, accelerated at the termination shock, and trapped within the heliosheath by the surrounding magnetic field. The other consisted of galactic cosmic rays, true interstellar particles arriving from outside the solar system entirely, partially blocked by the heliosphere but detectable even within it. As Voyager 1 approached the heliopause, the first population began to decline, while the second began to rise. This was precisely what the models had predicted would happen near the boundary. In May of 2012, the locally produced particle intensity dropped sharply and dramatically. Within days, it fell to nearly zero. At the same time, the galactic cosmic ray intensity jumped by a significant margin. This was a striking change, and it generated considerable excitement among the scientific team. It looked, in those first readings, as though Voyager 1 had crossed the heliopause and entered interstellar space. But something unexpected happened. The magnetic field direction did not change. The models had predicted that crossing the heliopause would produce a clear shift in the orientation of the local magnetic field, because the Sun's magnetic field and the interstellar magnetic field were expected to be aligned differently. Voyager 1's magnetometer showed no such shift. The field direction remained essentially unchanged on both sides of what the particle data suggested was a boundary. This was puzzling. Either the crossing had not actually occurred, or the interstellar magnetic field near the heliopause was oriented more closely with the Sun's field than any of the models had anticipated. Over the following months, the particle data continued to show the sharp changes that had appeared in May, with brief partial recoveries suggesting that the heliosphere was still breathing, expanding and contracting with solar activity, and that Voyager 1 was hovering near the boundary rather than definitively beyond it. Then, in late August of 2012, the plasma wave instrument aboard the spacecraft detected oscillations in the local plasma that allowed scientists to measure the density of the surrounding material directly. The density was approximately 40 times higher than it had been in the heliosheath, consistent with the known density of the local interstellar medium and inconsistent with any region within the heliosphere. This plasma density measurement, combined with the sustained changes in the cosmic ray data, provided the foundation for the announcement made in September of 2013, when NASA confirmed that Voyager 1 had entered interstellar space. The crossing was dated to around August 25, 2012. At that moment, Voyager 1 was approximately 121 astronomical units from the Sun, roughly 18 billion kilometers. The signal confirming the crossing had taken more than 16 hours to travel from the spacecraft to the receivers on Earth. The absence of a magnetic field direction change remained a subject of active discussion and research in the years following the announcement. Some researchers proposed that the interstellar magnetic field in the immediate vicinity of the heliopause had been draped and realigned by its long interaction with the heliosphere, so that it happened to be oriented similarly to the Sun's field in that particular region. Others suggested that the existing models of the interstellar magnetic field needed significant revision. The debate contributed to a broader reassessment of the heliopause's structure and pointed toward the complexity of the interaction between the heliosphere and the interstellar medium, an interaction that had been simplified in the models and turned out to be considerably more nuanced in reality. Voyager 2's crossing came in November of 2018, at a distance of approximately 119 astronomical units from the Sun, slightly closer than Voyager 1's crossing point, consistent with the heliosphere's known asymmetry. This crossing was in several ways more informative than Voyager 1's, partly because Voyager 2 still had a functioning plasma science instrument that could directly measure the properties of the plasma on both sides of the boundary. The instrument had stopped working on Voyager 1 in 1980, long before that spacecraft reached the heliopause, meaning that Voyager 1's crossing had to be inferred from indirect measurements. Voyager 2's crossing could be characterized with direct plasma data, providing a level of detail and certainty that complemented and extended what had been learned from Voyager 1. The direct plasma measurements confirmed the sharp transition from heliospheric to interstellar conditions. The solar wind speed dropped to effectively zero within a very short distance. The interstellar plasma density rose sharply. The magnetic field shifted. The transition happened over a distance of less than 1 astronomical unit, a remarkably abrupt change given the vast scales involved, suggesting that the heliopause is a well-defined and relatively thin boundary rather than a broad and gradual transition zone. One of the more notable findings from Voyager 2's crossing was the detection of a thin layer of unusually hot plasma just inside the heliopause, material that appeared to have been heated and compressed as it approached the boundary, forming a distinct zone between the general heliosheath conditions and the transition into interstellar space. This layer had not been clearly predicted by the models, and its discovery prompted new thinking about the processes occurring at the heliopause, including the possibility of magnetic reconnection events at the boundary releasing energy into the surrounding plasma. Together, the two crossings provided something no single spacecraft could have delivered: a comparison between two distinct points on the heliopause, separated in direction, measured years apart, by instruments that had been traveling and operating for decades. Where the crossings agreed, the agreement confirmed the broad theoretical picture of the heliosphere's outer edge. Where they differed, the differences pointed toward genuine variations in the heliosphere's structure and in the local interstellar environment immediately outside it. Both kinds of information, the confirmations and the surprises, represented exactly the kind of return that a mission of this scope and duration was designed to produce. Both Voyager spacecraft were now in interstellar space. They had crossed a boundary that no human-made object had ever crossed before, and in crossing it, they had not arrived anywhere. They had simply entered a new kind of emptiness, one that extended, in all directions, for distances that made the entire span of the solar system look like a brief preamble to something far larger and far harder to grasp. The crossing of the heliopause was not the end of the journey. It was the moment when the journey revealed its true scale. Everything that had come before, the launch, the planetary encounters, the decades of quiet transit through the outer solar system, had been a crossing of the neighborhood. What lay ahead, in every direction, was the open universe. And in that universe, the nearest landmark was so far away that the numbers required to describe the distance begin to lose their meaning almost immediately. Chapter 6. How far is far? There is a number associated with Voyager 1 that appears in nearly every article written about the spacecraft, and it is a number that resists genuine comprehension no matter how many times it is encountered. As of the mid-2020s, Voyager 1 is more than 23 billion kilometers from Earth. That figure is accurate. It is also, in any practical sense, meaningless to most people who read it. 23 billion kilometers is not a distance the human mind was shaped to understand. We evolved to navigate landscapes measured in meters and kilometers, to judge distances we could walk or ride or sail. Numbers in the billions applied to physical distance exist entirely outside the range of anything our intuition was built to handle. So it helps to approach the distance from a different direction entirely, building toward it through comparisons that begin somewhere familiar before moving outward into the genuinely incomprehensible. Light travels at approximately 299,792 kilometers per second. It is the fastest thing in the universe, and nothing we have ever built comes remotely close to matching it. A beam of light leaving Earth reaches the Moon in about 1 1/3 seconds. It reaches the Sun in roughly 8 minutes. It reaches Jupiter in anywhere from 33 to 53 minutes, depending on where the two planets happen to be in their orbits relative to each other. It reaches Saturn in about 70 to 90 minutes. These are already distances that stretch ordinary intuition considerably. The Moon feels close. The Sun feels distant but comprehensible. Jupiter and Saturn feel genuinely far. And yet all of these distances, placed beside the distance to Voyager 1, shrink into something that barely registers. A signal traveling at the speed of light takes more than 22 hours to travel from Earth to Voyager 1. Not 22 minutes. Not 22 hours on a slow day. More than 22 hours every day, as a baseline that grows longer with each passing week, as the spacecraft continues outward. When mission controllers at the Jet Propulsion Laboratory send an instruction to the spacecraft, they must wait more than 22 hours for it to arrive. Then they must wait another 22 hours for any response to return. The round trip for a single exchange takes nearly 2 full days. There is no possibility of real-time communication. Every interaction with Voyager 1 requires a patience that most modern communication systems have trained us to forget is even possible. To put that light travel time in perspective, consider that the entire width of the inner solar system, from the Sun out past the orbit of Mars, can be crossed by light in roughly 20 minutes. The distance to Voyager 1 is more than 60 times greater than that. The spacecraft is so far away that even describing its location in astronomical units, the standard measurement used for distances within the solar system, begins to feel inadequate to the task. At more than 160 astronomical units from the Sun, Voyager 1 sits at a distance where the Sun itself, seen from the spacecraft's vantage point, would appear as nothing more than an exceptionally bright star. Not a disk, not a source of warmth, not the overwhelming presence that it is from Earth. Just a point of light, far brighter than anything else in the sky, but a point nonetheless, indistinguishable in form from the thousands of other points of light scattered across the darkness in every direction. The spacecraft is traveling at approximately 17 kilometers per second relative to the Sun. That translates to roughly 61,000 kilometers per hour, a speed that would carry a traveler from one side of Earth to the other in under 40 minutes. By any terrestrial standard, it is an extraordinary velocity. A human being moving at that speed would experience the world as a blur. And yet, by the standards of interstellar space, 17 kilometers per second is almost imperceptibly slow. It is the speed of something that will spend tens of thousands of years covering distances that light crosses in years. This is where the scale begins to reveal itself in its full weight. The nearest star system to our own is Alpha Centauri, a system of 3 stars located approximately 4.37 light-years from the Sun. 1 light-year is the distance light travels in a single year, approximately 9.5 trillion kilometers. Alpha Centauri is therefore roughly 41 trillion kilometers away. At Voyager, one's current speed of 17 kilometers per second, covering that distance would take approximately 73,000 years, not 73,000 days, not 73,000 months, 73,000 years, a span of time longer than the entire recorded history of human civilization, multiplied many times over, required simply to reach the nearest neighboring star system. And Voyager 1 is not heading toward Alpha Centauri. Its trajectory carries it in a different direction entirely, toward the constellation Ophiuchus. The nearest star in roughly that direction is considerably further away than Alpha Centauri. The spacecraft will not make a close approach to any star for roughly 40,000 years, when it will pass within about 1.6 light-years of a dim red dwarf called Gliese 445. 1.6 light-years is not a close approach in any meaningful sense. It is still an enormous distance, but it is the nearest thing to a stellar encounter that Voyager 1's trajectory produces within any time frame that can be described without the numbers becoming entirely abstract. What these figures reveal, when held together, is something that no single number can convey on its own. The solar system, for all its vastness, for all the decades it has taken Voyager to cross even its outer regions, is not a significant fraction of the distance to the nearest star. Voyager 1 has been traveling for nearly 50 years. It has covered a distance that takes light more than 22 hours to cross, and it has traveled approximately 0.002 light-years. The nearest star is 4.37 light-years away. The distance Voyager has covered in 50 years of continuous travel represents less than 0.1% of the distance to the nearest stellar neighbor. If you were to represent the solar system on a piece of paper, drawing the sun in the center and marking the current position of Voyager 1 at the edge of the page, the nearest star on that same scale would be somewhere across the room, possibly across the building. The distances involved are not merely large in the way that geographic distances on Earth are large. They are large in a way that breaks the ordinary relationship between effort, time, and progress. Voyager has been traveling continuously at speeds no human being has ever personally experienced for half a century, and it has barely begun to cross the gap between our solar system and its nearest neighbor. This is the terrifying reality that the Voyager journey reveals, and it is worth being precise about what makes it terrifying. It is not danger. It is not the hostility of space, though space is certainly hostile to biological life. What is genuinely unsettling about this scale is what it implies about our position in the universe and about the practical limits of everything we might ever attempt to do beyond our own solar system. We have sent our fastest spacecraft outward for 50 years, and the nearest star remains so far away that the concept of reaching it within any civilization's lifetime, using anything resembling our current technology, is not a practical possibility. It is a mathematical near impossibility. The universe is not merely large, it is large in a way that is specifically, precisely, almost cruelly mismatched with the tools available to us. The speed of light, which feels impossibly fast from a human perspective, is in practice an agonizingly slow way to cross interstellar distances. Voyager travels at roughly 1/50,000th the speed of light. Even at the speed of light itself, reaching Alpha Centauri would take 4 1/3 years. Reaching the center of the Milky Way would take 26,000 years. Reaching the Andromeda Galaxy, our nearest large galactic neighbor, would take 2.5 million years. The universe is so large that even its own speed limit, the fastest anything can travel, is nowhere near fast enough to make it feel traversable within any time frame that biological creatures can meaningfully inhabit. Voyager 1 did not reveal this. The mathematics were always there, available to anyone who chose to work through them. What Voyager did was make those mathematics concrete. It gave the numbers a physical embodiment. A small machine, built by human hands, traveling as fast as human engineering has ever managed to propel anything, and still spending 50 years to cross a distance that represents an almost negligible fraction of the gap to the nearest star. The scale of the universe is not an abstraction when something is actually out there in it, moving, and the numbers describing its position and its remaining distance from any destination are updated every day. 23 billion kilometers, more than 22 light hours, less than 0.1% of the way to the nearest star, still traveling, still receding. The distance growing by roughly 1.5 million kilometers every day, and still, by cosmic standards, barely gone. Chapter 7. The Nearest Star. The nearest star to our Sun has a name that most people have encountered, but few could place precisely in the sky. Proxima Centauri is a small, dim red dwarf, the faintest member of the Alpha Centauri system, located approximately 4.24 light-years from Earth. It is the closest known star to our own, and it has become a reference point in almost every serious discussion of interstellar distance, because it represents the minimum scale of the problem facing anyone who wants to think honestly about travel between stellar systems. 4.24 light-years sounds like a manageable number until you begin to unpack what it means. A light-year, as noted earlier, is the distance light travels in a full year, approximately 9.5 trillion kilometers. Multiply that by 4.24, and the result is roughly 40 trillion kilometers. 40 trillion. Written out in full, that number contains 13 digits. It is a distance so large that the familiar tools of human spatial intuition simply stop functioning. You cannot visualize 40 trillion kilometers. You cannot feel it, cannot walk it, cannot drive it, cannot fly it in any aircraft ever built. You can only calculate it, and then sit with the result and try to absorb what it implies. Voyager 1, the fastest traveling object humanity has ever launched, moving at 17 kilometers per second, would need approximately 73,000 years to cover that distance. If it were heading toward Proxima Centauri, which it is not, the spacecraft is moving in a different direction, and the stars it will pass nearest to over the next several 100,000 years are all considerably further away than Proxima Centauri. The 40,000-year figure for its closest stellar approach. The pass, within 1.6 light-years of Gliese 445, represents an encounter with a star that is itself further from us today than Proxima Centauri, and the approach distance of 1.6 light-years is still 15 trillion kilometers. A near miss, in interstellar terms, is still an almost incomprehensible distance. It is worth pausing on what Proxima Centauri actually is, because the name carries a weight of expectation that the reality does not entirely support. It is not a star like our Sun. It is a red dwarf, a small, cool, dim star containing roughly 1/8 the mass of the Sun, and emitting only a tiny fraction of the Sun's luminosity. It is so faint that it cannot be seen with the naked eye from Earth, despite being the nearest star. Its surface temperature is considerably lower than the Sun's. It burns slowly and will continue burning for an estimated 4 trillion years, far longer than the current age of the universe, which stands at roughly 13.8 billion years. Red dwarfs are extraordinarily long-lived by stellar standards, and they are also extraordinarily common. The majority of stars in the Milky Way are red dwarfs. If our galaxy has a typical stellar population, then most of the stars in the universe are small, dim, slow-burning objects like Proxima Centauri. Proxima Centauri is known to host at least one planet in its habitable zone, a world designated Proxima Centauri b, detected through the radial velocity method in 2016. Whether that planet has conditions suitable for life as we understand it is a question that current technology cannot answer definitively. Red dwarf planets face challenges that planets around Sun-like stars do not. Red dwarfs are prone to powerful stellar flares that could strip away planetary atmospheres over geological timescales. Planets in the habitable zone of a red dwarf orbit so close to their star that they are likely tidally locked, keeping one face permanently toward the star and one permanently away. Whether life could arise and persist under such conditions remains genuinely uncertain. But the question of life on Proxima Centauri b, interesting as it is somewhat beside the point when considering what the distance to that system means for any possibility of human exploration. Even if Proxima Centauri b were confirmed to harbor complex life, even if it were confirmed to be a world broadly similar to Earth in its conditions, the distance to it would remain exactly what it is: 73,000 years at Voyager's speed, 4 1/3 years at the speed of light, which is physically unattainable for any object with mass. The existence of something interesting at that distance does not make the distance smaller. It only makes the impossibility of reaching it more poignant. This is one of the more quietly devastating implications of the Voyager journey, and it deserves to be stated plainly. We now know with reasonable confidence, that planets exist around nearby stars. We know that some of those planets orbit in regions where liquid water could exist on their surfaces. We know that the chemical building blocks of life are present throughout the galaxy, carried in interstellar gas clouds and distributed by dying stars across billions of years of cosmic history. The ingredients for life appear to be common. The conditions for life may be common. And the nearest examples of potentially habitable worlds are so far away that traveling to them with anything resembling current or near-future technology is not a realistic possibility within the lifetime of any civilization that has ever existed on Earth. The Milky Way contains somewhere between 100 billion and 400 billion stars. The distances between them across the entire galaxy follow the same general pattern as the distance between the Sun and Proxima Centauri. Measured in light years, traversable by light in years, but by spacecraft in tens of thousands of years per hop. The galaxy is approximately 100,000 light years across. A spacecraft traveling at Voyager's speed would need roughly 2 billion years to cross it from one side to the other. The universe, at its larger scales, contains hundreds of billions of galaxies, separated by distances measured in millions and billions of light years. The numbers do not become more manageable with repetition. They become, if anything, more insistent in their refusal to yield to human intuition. Every time the scale is approached from a new angle, it reasserts itself with the same quiet finality. Space is not merely large. It is large in a way that appears specifically designed to confound any attempt to travel through it on timescales meaningful to biological creatures. Whether that appearance reflects something deep about the nature of the universe, or simply the accident of our particular position and capability within it, is a question that physics and philosophy share, but neither has fully answered. What Voyager 1 contributes to this picture is not new mathematics. The distances to nearby stars were known long before the spacecraft launched. What it contributes is a kind of physical testimony. There is something genuinely different about knowing that an object built on Earth has been traveling continuously for 50 years and has covered less than 0.1% of the distance to the nearest star. The abstraction becomes concrete, the calculation becomes a journey, and the journey, followed in real time over decades, makes the scale of the universe feel less like a number in a textbook and more like a condition of existence, something that was always true, always present, and that the Voyager mission has simply made impossible to look away from. Proxima Centauri will still be burning in 4 trillion years. The light it emits right now is already traveling toward Earth and will arrive in just over 4 years. In that same 4 years, Voyager 1 will have covered roughly 2 billion kilometers, approximately 1/200th of the distance that light will cross in the same period. The star is there, the distance is real, and between here and there lies a volume of space so vast and so empty that the most distant human-made object in existence, after 50 years of travel, has barely entered it. Chapter 8. What Lies Ahead? Voyager 1 is in interstellar space. That much is confirmed. But it hasn't left the solar system, at least not in every sense that phrase can meaningfully carry. The question of where the solar system ends depends entirely on how you define it, and different definitions give answers so different from one another that the question itself begins to reveal something important about the nature of boundaries in space, which is that most of them are not lines at all, but gradients, transitions, zones where one set of conditions gives way to another across distances that dwarf anything in ordinary human experience. If the solar system is defined by the reach of the solar wind, Then Voyager 1 crossed its boundary in 2012 when it passed through the heliopause. By that definition, the spacecraft has been in interstellar space for over a decade, sampling the local interstellar medium and returning data from beyond the Sun's direct physical influence. But if the solar system is defined by the reach of the Sun's gravity, by the extent of the region within which objects are gravitationally bound to the Sun and travel on orbits that are primarily shaped by the Sun's pull, then both Voyager spacecraft have a very long way to go before they can be said to have truly departed. Gravity does not have a sharp boundary the way the solar wind does. It diminishes with distance according to the inverse square law, growing weaker and weaker, but never reaching zero. At the distance Voyager 1 has currently reached, the Sun's gravitational pull is extraordinarily weak, far too weak to significantly influence the spacecraft's trajectory over any short timescale. But it is still the dominant gravitational force in the local environment. There are no nearby stars whose gravity competes meaningfully with the Sun's at that distance. In the gravitational sense, Voyager is still, technically, a member of the solar system. The outer boundary of the Sun's gravitational domain is thought to be marked by a vast and distant structure called the Oort cloud. This is a spherical shell of icy bodies believed to surround the solar system at distances ranging from roughly 2,000 to 100,000 astronomical units from the Sun. To appreciate what those numbers mean, recall that the heliopause, the boundary Voyager 1 crossed in 2012, lies at approximately 121 astronomical units. The inner edge of the Oort cloud is estimated to begin at roughly 2,000 astronomical units, more than 16 times further from the Sun than the heliopause. The outer edge of the Oort cloud may extend to 100,000 astronomical units, nearly 1,000 times further out than the heliopause, and roughly 1.5 light years from the Sun. Voyager 1 will reach the estimated inner edge of the Oort cloud in approximately 300 years, assuming current estimates of the cloud's inner boundary are accurate. It will take the spacecraft approximately 30,000 years to pass through the Oort cloud entirely and emerge on the far side. During that entire transit, the spacecraft will almost certainly be silent. Its power will have been exhausted long before it reaches the Oort cloud's inner edge. Its instruments will be dark. Its transmitter will have fallen quiet sometime in the late 2020s or early 2030s, depending on how carefully the remaining power is managed. The golden record it carries will continue outward regardless, a physical artifact traveling in silence through one of the most remote regions of the solar system's extended gravitational domain. The Oort cloud itself has never been directly observed. No telescope has resolved individual Oort cloud objects in their distant orbits. Its existence is inferred primarily from the behavior of long-period comets. Comets that arrive in the inner solar system from random directions with orbital periods of hundreds or thousands of years, on trajectories that indicate they originated in a roughly spherical distribution of objects surrounding the solar system, rather than in the flattened disk of the ecliptic plane. Occasional gravitational perturbations, caused by passing stars or by the tidal influence of the galactic disk itself, dislodge objects from the Oort cloud and send them falling inward on long elliptical trajectories that eventually bring them close to the Sun, where we observe them briefly as comets before they retreat again into the outer dark. The objects in the Oort cloud are believed to have originated much closer to the Sun, in the region where the giant planets were forming roughly 4.5 billion years ago. During that early period of the solar system's history, gravitational interactions with the forming giant planets, particularly Jupiter and Saturn, which were by far the most massive objects in the system after the Sun itself, flung enormous numbers of small icy bodies outward on highly elliptical orbits. Over vast timescales, the gravitational influence of passing stars and the galactic tide gradually rounded out the most elongated of those orbits, producing the roughly spherical distribution that characterizes the Oort cloud today. The objects themselves are pristine survivors of the early solar system, composed of the same ices and rocky materials that were present when the planets first began to form, preserved in deep cold at distances so extreme that the Sun's warmth has never meaningfully reached them. What this means for Voyager is that when the spacecraft signal finally falls silent, when the last transmission is received and processed and archived, the journey will not end. The spacecraft will continue outward through the Oort cloud for 30,000 years, moving in complete silence through a region populated by ancient icy bodies on orbits so large that a single orbit takes millions of years to complete. It will pass through this region without making any close approach to any individual object, because the Oort cloud, despite containing an estimated trillion or more individual bodies, is so vast that the space between those bodies is, on average, enormous. The cloud is dense only by interstellar standards. By any terrestrial measure of density, it is effectively empty. Beyond the outer edge of the Oort cloud, roughly 1.5 light-years from the Sun, Voyager 1 will finally exit the solar system in the fullest gravitational sense. It will enter a region where the Sun is just another star, where its gravity competes on roughly equal terms with the gravitational influences of neighboring stellar systems, where the objects one encounters, if one encounters any, are not bound to the Sun and are not part of any structure that can meaningfully be called our solar system. This transition will occur, if current trajectory calculations are correct, in approximately 40,000 years, the same time frame as the closest stellar approach to Gliese 445. After that encounter, which is not really an encounter in any meaningful physical sense, since 1.6 light-years is still 15 trillion kilometers, Voyager 1 will continue outward into the galaxy. Its trajectory from that point will be shaped gradually by the gravitational influences of stars it passes relatively near over millions and billions of years, none of which will come close enough to significantly deflect its path in any short time frame. It will drift through the Milky Way as the Milky Way itself continues its own slow rotation, as stars are born and die around it, as the galaxy gradually evolves over timescales so long that the current configuration of the night sky will be unrecognizable long before Voyager has traveled any significant fraction of the distance to the galactic center. In roughly 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to expand into a red giant, eventually engulfing the inner planets including Earth. Whether anything resembling human civilization will exist at that point to observe this event is, of course, entirely unknown. What is known is that Voyager 1 will still be out there, somewhere in the galaxy, long after the Sun has completed its entire life cycle. The golden record it carries, protected from corrosion by the vacuum of space and from decay by the absence of any chemical environment capable of breaking it down, is expected to remain largely intact for at least 1 billion years. The information encoded on it, the sounds of Earth, the greetings in 55 languages, the music, the images, the mathematical diagrams pointing back to a small planet orbiting an ordinary star, will persist in physical form long after every trace of the civilization that created it has vanished. There is something in this that resists easy description. Voyager 1 will outlast its makers. It will outlast the institutions that funded and supported it, It will outlast the languages spoken by the people who built it. It will outlast, in all likelihood, the species that launched it. And it will do all of this not through any remarkable durability of its own. It is, after all, a machine built in the 1970s with the engineering standards of that era, but simply through the absence of anything in interstellar space capable of stopping it or degrading it significantly on any timescale shorter than geological. In space, things persist not because they are strong, but because there is nothing around them to cause them to fail. What lies ahead for Voyager 1 is, in the most literal sense, everything. The entire galaxy. Billions of years of travel through a universe that will continue expanding and evolving long after the spacecraft has lost any connection to the world that built it. It will travel through regions of the galaxy we have never observed closely, past stars that have not yet formed, through clouds of gas and dust that are, right now, slowly condensing under their own gravity toward the ignition points of future suns. It will carry, in silence, a record of a moment in the history of one small planet. A moment when something on that planet became curious enough about the universe to reach outward into it, and patient enough to keep listening for as long as the power held out. Chapter 9. The Golden Record. Attached to the frame of each Voyager spacecraft, mounted in a way that would survive the rigors of launch and the decades of travel through space, is an object that has nothing to do with planetary science or heliospheric physics, or the measurement of cosmic ray intensities in the interstellar medium. It is a 12-inch gold-plated copper disc, a record, in the most literal sense of that word, of a moment in the life of a planet. It was placed there by a group of people who understood, with unusual clarity, that the spacecraft carrying it would travel indefinitely through space long after its scientific instruments had fallen silent, and who felt that this fact warranted some kind of response beyond the purely technical. The Golden Record, as it has come to be known, was assembled under the direction of the astronomer Carl Sagan, who chaired the committee responsible for its contents. Sagan was a scientist of genuine distinction, but he was also someone who thought carefully about what science meant in a broader human context, about the relationship between scientific knowledge and the experience of being alive, about the place of human civilization in the larger story of the cosmos. The Golden Record was, in many ways, an expression of those concerns given physical form. The record contains 115 images encoded in analog form, representing human anatomy, mathematical concepts, the structure of DNA, the solar system, and scenes from life on Earth, including landscapes, plants, animals, and people going about ordinary activities. It contains greetings spoken in 55 languages, ranging from the most widely spoken languages on Earth at the time to several that were already rare or endangered. It contains natural sounds, wind, rain, surf, thunder, the calls of birds and whales and other animals, the sounds of human activity including footsteps, laughter, and the crying of an infant. It contains 90 minutes of music drawn from cultures across the world and across recorded human history, including works by Johann Sebastian Bach, Wolfgang Amadeus Mozart, and Ludwig van Beethoven, alongside traditional music from dozens of cultures that receive far less attention in Western-dominated accounts of musical history. It also contains something more unusual. The record includes a brainwave recording of Anne Druyan, who was at the time the creative director of the Golden Record project and who would later marry Carl Sagan. Druyan has described the content of her thoughts during the recording. She was thinking about the history of civilization, about the challenges facing humanity, and by her own account, about falling in love. The recording captures the electrical activity of her brain during that meditation, translated into audio form and included on the record as a kind of intimate human document. A record not just of what humans had made and thought and felt in general, but of what one particular human was thinking and feeling at one particular moment in time. The cover of the record is engraved with instructions for playback, written not in any human language, but in the symbolic language of physics and mathematics. The instructions use the hyperfine transition of hydrogen, a fundamental physical process whose frequency is the same everywhere in the universe, as a unit of time and length, providing a reference frame from which a sufficiently advanced finder could, in theory, reconstruct the images and sounds encoded on the disk. Diagrams indicate the location of the solar system relative to 14 known pulsars, each with its characteristic pulse frequency encoded, so that the record's origin can be triangulated by anyone with sufficient knowledge of pulsar astronomy. The cover also shows a diagram of the record itself and the stylus needed to play it, along with a representation of the hydrogen spin-flip transition that defines the units used throughout. The practical probability that the golden record will ever be found by anyone is, by any honest assessment, vanishingly small. Voyager 1 is not heading toward any star system that is known to harbor intelligent life, or toward any star system at all within any time frame shorter than tens of thousands of years. The galaxy contains an estimated 100 billion to 400 billion stars, distributed across a disk roughly 100,000 light-years in diameter. The chance that a small spacecraft drifting on a trajectory determined by a planetary alignment in the late 1970s will happen to pass close enough to an inhabited world for its cargo to be discovered is not zero, but it is extraordinarily close to zero on any timescale that human imagination can comfortably hold. Sagan and his colleagues knew this. They were not naive about the odds. The decision to include the record was not based on a realistic expectation of it being found. It was based on something else. A recognition that the act of sending it said something true and important about the civilization that launched it, regardless of whether anyone ever received it. What the golden record represents, in this reading, is a statement of existence made in the full knowledge that it may never be heard. It is the acknowledgement, cast in gold and copper and launched into the darkness, that something on the third planet of an ordinary star in an unremarkable part of the Milky Way had become aware of the universe around it, had spent centuries studying that universe with increasing precision and care, and had chosen, when given the opportunity, to send something beyond the boundaries of the known, to include music, to include laughter, to include the sound of rain and the songs of whales, and the recorded electrical activity of a human brain in the act of falling in love. There is a tradition in human culture of leaving messages for the future. Letters sealed in time capsules, inscriptions carved in stone, books written with the explicit understanding that the author will not live to see most of their readers. The golden record belongs to this tradition, but extends it to a scale that no other human artifact has ever approached. A time capsule buried in a city park might be opened in 100 years. The golden record will still be traveling in 1 billion years, in a galaxy that will have changed beyond recognition, carrying its contents through a darkness that has no memory of the civilization that placed them there. This is not a melancholy observation, though it can feel like one. It is, in a different light, one of the most remarkable things about the human species. This impulse to reach outward, to communicate, to leave a record of having been here, even when the chances of that record being received are negligible and the timescales involved swallow the very concept of purpose. The golden record was not made because anyone expected it to succeed in its ostensible mission. It was made because making it was the right response to the opportunity, because the people who built Voyager understood that they were sending something into a future they could not see, and they chose to make that something carry more than instruments. Carl Sagan wrote about the golden record and about the Voyager mission in terms that have stayed with many people who encountered them. He described the pale blue dot image, the photograph taken by Voyager 1 in 1990, looking back at Earth from a distance of roughly 6 billion kilometers, as a demonstration of the cosmic insignificance of everything humanity had ever done or been, and simultaneously as an argument for treating this small world and its inhabitants with more care and more generosity than we typically manage. The image showed Earth as a point of light smaller than a single pixel, suspended in a sunbeam, surrounded by the immensity of space in every direction. Everything that has ever happened in human history, every war and discovery and love affair, an act of cruelty and moment of grace, occurred on that point of light. The golden record is the other side of that image, where the pale blue dot shows what we look like from the outside, small, isolated, temporary. The golden record represents what we chose to say about ourselves when given the chance to say something. It is our answer to the question that the scale of the universe implicitly poses, which is not whether we matter in any cosmic sense, but what we choose to do with the brief, improbable fact of our existence. The answer encoded on that gold-plated disc is, in its way, a generous one. We chose music. We chose greetings in 55 languages. We chose the sound of rain. We chose to include a recording of a human being thinking about love. Whether that answer reaches anyone is, in the end, beside the point. The reaching is the point. The decision to include something of ourselves in what we were sending outward, to acknowledge across the darkness that we were here and that we had found the universe worth paying attention to. That decision says something about what we are that no purely scientific instrument could convey. The golden record travels on, in silence now, past the last signals the spacecraft can send, past the reach of anything we can follow or track or measure, carrying forward into an open future, the most human thing about the most distant journey humanity has ever made. Chapter 10. Still traveling. There is a signal traveling toward Earth right now that left a spacecraft more than 22 hours ago. It is moving at the speed of light, crossing a distance that no human being has ever physically traversed, and that none will in any foreseeable future. By the time it arrives, it will be received by one of the large dish antennas of NASA's Deep Space Network, amplified to the point of usability from a power level so faint it has no meaningful everyday equivalent, decoded by equipment maintained specifically for the purpose, and passed to a small group of people who will read it the way a careful observer reads any long-running record, looking for changes, for continuities, for anything that requires attention or response. This has been happening, with only brief interruptions, for nearly 50 years. The signal has been coming in, the team has been listening, and the data has been accumulating. Not dramatically, not with the fanfare that attended the planetary encounters of the late 1970s and early 1980s. Quietly, patiently, in the way that most genuinely significant things happen when they are allowed to unfold at their own pace, rather than being forced into the rhythms of news cycles and public attention spans. The team that maintains contact with both Voyager spacecraft today is small. A handful of engineers and scientists who divide their time between Voyager and other missions, working with documentation that predates modern computing environments and with a spacecraft architecture that was obsolete by the standards of personal computing before most of them entered the workforce. The computers aboard Voyager 1 carry approximately 69 kilobytes of memory. A single uncompressed image taken by a modern smartphone contains more data than Voyager's computers can store. And yet, those computers have been running without interruption for nearly 50 years, executing instructions sent from Earth across distances measured in light hours, managing a spacecraft that has outlasted the careers of everyone who originally built it. The power situation, as the mission moves through the mid-2020s, is the defining constraint on everything that remains. The radioisotope thermoelectric generators that have powered both spacecraft since launch are producing roughly 40% less electricity than they did in 1977. The decline is predictable. It follows the known decay rate of plutonium-238, but it is also irreversible. Every year, the available power budget shrinks by a small but non-negligible amount, and every year the mission team must make decisions about which systems to keep running and which to sacrifice. Heaters that once protected instruments from the cold of deep space have been turned off. Instruments that served their purpose during the planetary encounters were shut down decades ago. What remains is a carefully managed minimum. The systems needed to keep the spacecraft oriented, the transmitter running, and the few remaining scientific instruments gathering the data that only these two spacecraft are positioned to collect. In 2023, Voyager 1 developed a significant anomaly that illustrated both the fragility and the resilience of the mission in equal measure. The spacecraft began returning garbled data, a repeating pattern of signals that carried no scientific or engineering information, suggesting that something had gone wrong with one of the computers responsible for formatting the outgoing data stream. The signal itself was intact. The spacecraft was clearly still functioning and still transmitting, but the content of what it was sending was unreadable. The engineering team spent several months carefully diagnosing the problem, sending commands and waiting the 44+ hours required for each round-trip exchange, building up a picture of the fault from the limited information available. Eventually, they traced the issue to a single corrupted chip in the flight data system, a component that had been running continuously since 1977 and that had, after nearly half a century of exposure to the cosmic ray environment of interstellar space, developed a region that could no longer reliably store the code it was supposed to hold. The chip had not failed entirely. It had simply degraded in a specific and diagnosable way, and the team developed a solution that involved relocating the affected software to other parts of the computer's memory, a process that had to be executed in carefully sequenced steps, each one transmitted across more than 20 billion kilometers and verified before the next was sent. The repair took months. It succeeded. In the spring of 2024, Voyager 1 resumed returning usable data from interstellar space, its instruments once again measuring the plasma and magnetic field conditions of the local interstellar medium, and sending those measurements home across a distance that grows by roughly 1.5 million kilometers every day. The episode was, by any measure, a remarkable piece of remote engineering. It was conducted on a computer architecture that no university currently teaches, across a communication delay that makes real-time problem-solving impossible, by a team working from documentation that is decades old and from the accumulated institutional memory of a project that has been running longer than most of its current participants have been alive. What the 2023 anomaly also illustrated was something about the emotional texture of working on a mission of this duration and character. The people who work on Voyager are not indifferent to the spacecraft they tend. They cannot be, after years or decades of sustained attention to something so remote and so singular. When the signal went garbled, the distress felt by the team was genuine. When it came back clean, the relief was equally genuine. These are not sentimental projections onto an indifferent machine. They are the natural consequence of care sustained over long periods of time. You cannot spend years listening to something, worrying about it, solving its problems from a distance of 20 billion kilometers, without developing something that functions, in practice, very much like a relationship. This is one of the more unexpected dimensions of the Voyager story, and it is one that the purely technical accounts of the mission tend to underemphasize. The spacecraft are old. The technology aboard them is ancient by modern standards. The data they return, while scientifically irreplaceable, arrives at rates that would have seemed laughably slow to any engineer working with contemporary systems. And yet, the mission persists, supported by people who understand that what Voyager provides, it provides uniquely, that no other instrument is currently positioned to make the measurements these two spacecraft are making, and that when the signals finally stop, that particular window into the local interstellar medium will close permanently. The end of the mission, when it comes, will not be dramatic. There will be no planned shutdown command, no final ceremonial transmission, no moment of deliberate farewell. The power will simply decline below the threshold needed to sustain the transmitter, and the signal will stop. The team will have been watching the power budget closely enough to know that the end is approaching, and the last few transmissions will be received with the awareness that they may be among the final ones. But there will be no way to know, from the data itself, that any given transmission is the last. The spacecraft does not know it is dying. It will simply, at some point, fall silent, and the silence will accumulate until it becomes clear that no further signal is coming. After that silence falls, the spacecraft will continue. This is perhaps the most important thing to understand about what happens at the end of the Voyager mission. The end of the mission is not the end of the journey. The journey has no end, at least not on any timescale that human civilization can meaningfully contemplate. The spacecraft will travel outward through the Oort cloud for 30,000 years. It will make its closest approach to Gliese 445 in 40,000 years. It will continue through the galaxy for billions of years after that, long after the sun has exhausted its fuel and expanded into a red giant, long after the Earth has ceased to exist in any form recognizable to the creatures that currently inhabit it. The golden record will travel with it, silent and intact, through all of that. In the vacuum of interstellar space, with no atmosphere to cause corrosion and no liquid water to facilitate chemical decay, the record is expected to remain physically intact for at least 1 billion years. The information encoded on it, the sounds, the images, the greetings, the music, the brainwave recording of a human being thinking about love, will persist in recoverable form for a span of time that makes the entire history of life on Earth look brief. Whether anything will ever exist anywhere in the galaxy with the capability and the curiosity to find that record and decode it is a question that cannot be answered. It may never be answered. The universe does not owe us a recipient for our messages, but the record travels on regardless, and in traveling on, it carries forward something that the numbers and the physics and the engineering cannot fully capture. The fact that the people who built Voyager and launched it and tended it for 50 years were not merely conducting a scientific mission. They were also, in some sense, that resists precise definition, reaching out, reaching towards something they could not see, across distances they could calculate but never truly feel, with a message they had no reason to expect would be received, and every reason to send anyway. This impulse, to reach outward, to communicate, to mark the fact of having existed in a universe so vast that existence itself seems improbable, is not unique to the Voyager mission. It runs through the entire history of human exploration and expression. But Voyager gives it a physical form and a physical scale that nothing else in human history has matched. The spacecraft is out there right now, moving through darkness that has no name, carrying its record and its silent instruments past stars that will not form for millions of years, through regions of the galaxy that no human eye has ever seen and none ever will. And it got there because a group of people in the 1970s decided to aim something at the darkness and keep listening for as long as the power held out. The power is nearly gone now. The listening is nearly over. The journey is just beginning. There is something worth sitting with in that image as you settle towards sleep. Somewhere beyond the reach of any telescope, beyond the boundary of the sun's influence, beyond the edge of everything we have ever directly touched or sampled or seen, two small machines are moving through the dark. They are moving right now, at this moment, as you read these words. They have been moving continuously since 1977, and they will continue moving long after every person alive today has been gone for millions of years. They carry, between them, two copies of a golden record that contains the sound of rain, the songs of whales, the music of Bach, and the electrical record of a human brain thinking about love. They are the furthest things humanity has ever made. They are the quietest possible argument for the idea that curiosity, sustained over long enough periods and pointed in the right direction, is one of the most extraordinary things the universe has managed to produce. And they are still out there, still traveling, still carrying forward the reach of a species that looked up at the stars and decided, against all practical odds, that the darkness was worth sending something into. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.